This is a video about two related topics, simplifying radicals and an introduction to imaginary numbers. If we have root 12, you could put that in your calculator and you'd get some sort of decimal because clearly 12 does not have an exact square root. But in algebra, we would not leave this as root 12. There are ways to simplify it because we could split this into two things, root 4 times root 3. Root 4 times root 3 makes root 12. And root 4, of course, can be simplified. That's just 2. So this would be the form that would be considered simplified and that you would put for an answer on a test or use as you went along in a question. So there's a couple of different techniques that could get you here. Some people would go about this slightly differently. And I want to show you both techniques so that you can choose what works best for you. Some would say, well, I could split this into, let's say, root 2 and root 6. And then 6, I can split 6 into 2 and 3. So this would be like root 2 and root 3. And I'll just circle for clarity here that these would sort of be my results at the end. The root 6 was just a midway step. And so you might say, okay, well, if I have root 2 times root 2, that gives me a 2. And then root 3 on its own is root 3. Okay, so same answer. Why was the one on the left a little bit quicker? Well, the one on the left was quicker because I separated root 12 into a number that specifically has a square root. In other words, a number that is a perfect square. 4 is a perfect square. Whereas on the right side here, the two numbers that I separated 12 into, 2 and 6, neither one of those has a perfect square. Pardon me, neither one of them is a perfect square. So I had to keep going. What we can see from this is that if you can separate a radical into a number that is a perfect square, a number that has a square root, you kind of save a step. That means that really there's only certain numbers that are worth pulling out of a radical. Those numbers are numbers that are perfect squares. So if you can get like root 4, root 9, root 16, root 25, and I could keep going with this, but these are the numbers that are really worth pulling out of a radical. Because again, if you pull out numbers that are not perfect squares, numbers that don't have a square root, well, then you got to separate them and separate them. So these are the numbers we're really looking for. Let's try another example. Let's say we do root 48. Pause this video for a moment if you need to, and figure out which of these perfect squares, and in fact, what's the biggest of these perfect squares that goes into 48. And the result would be, 4 does, by the way, it would be root 4 times root 12. But there's a bigger one that goes in, which is 16. You can split 48 into root 16 and root 3. And if you see that, well, then you're pretty much done immediately. Let's say you had, by the way, split this into root 4 and root 12, because that's 48. Okay, you'd have 2 root 12, but then you'd have to go and separate 12 into root 4 and root 3. So you'd get there. You'd get to the exact same place because you'd have 2 and then another 2 from here. So you'd end up in the same place. But of course, we're trying to make this as short and quick as possible. You can see that finding the largest perfect square that goes into this number is really what we want to do. That makes the whole thing done in like one step, basically. So let's do a couple more of these. Let's say root 54. Again, pause the video if you need to. Find the biggest perfect square that goes into 54. These are the numbers we're choosing from, etc. The biggest one that goes in here would be 9. 9 goes into 54. We can separate this into root 9 times root 6, and we end up with 3 root 6. That would be the simplified version of root 54. Okay, a couple more for practice here. Let's do root 42 and root, what do we want to do? Root 80. Again, pause, try those two. Okay. Root 42. Well, there's plenty of things that go into 42, 2 and 6 and 7. There are no perfect squares that go into 42, though. If we keep going with this list, you can see we're now bigger than 42 and nothing's gone in yet. This can't be simplified because there are no perfect squares that go into 42. If you separate it into root 2, root 21, root 3, root 7, there's nothing there. But we don't need to do all this. We can just see immediately none of those perfect squares go into root 42. So that's the final simplified version. There's nothing more to do. Root 80, on the other hand, there is something that goes into 80 from this list. It's 16. We can separate this into root 16 and root 5, which is 4 root 5. Now, maybe you saw that 16 goes into 80. Maybe not. Let's say that you didn't. That's okay. You can use that other technique that we kind of mentioned at the beginning and just keep on separating this. Okay, so we'll do, and if you're going to do it this way, it's easiest just to kind of pull out the smallest number you can each time. So like 2 goes into 80. Okay, great. 2 and 40. 2 goes into 40. Great. 2 and 20. 2 goes into 20. So 10, 2 goes into 10. And now we're done because there's nothing to split root 5 into. So again, I'll circle sort of the ones that we actually stopped on, just for clarity. And so we can put these together now, like root 2 times root 2, that makes 2. Root 2 times root 2, that also makes 2. And then we have this root 5. So we end up with 2 times root 5. In other words, 4 root 5. But again, we'll point out how much quicker it is if we can see the first time around the biggest perfect square that goes into the number we're starting from. If we can see that 16 is the biggest perfect square that goes into 80, boy, we're done in one step instead of, I don't know, 6 or 7. So that's simplifying radicals with positive numbers. So now we're going to switch gears a little bit into something that, well, you may have done before, but it's a little bit different because most likely up until now in math, if you see, let's say, the square root of -8, there's no such thing, and you say there's no solution or it's impossible. But we're going to change that a little bit now by introducing imaginary numbers. They're imaginary because they don't really exist. Like there really isn't a number that you can square to get -8, or even something like square root of -4. Like 4 has a square root, but -4, there isn't really something that you can square to get -4. This is why it's an imaginary number. So here's the definition of what we're talking about. There's one imaginary number, it's called I. And the way it's defined is this. That's the official definition of it. I is the imaginary number that if you squared it, theoretically would give you -1. Now, the way that you'll probably remember it is as I equals the square root of -1, but technically, like if you asked a real mathematician, this doesn't make sense because there is no square root of -1. This definition does make sense because it's the imaginary number that hypothetically, if you did square it, gives you -1. But really, either way you want to remember this is fine. And so here's how it works. Anytime that we have, and I'll start with the square root of -4. Anytime that we have the square root of a negative, just like we split them up on previous pages and previous questions, we're going to split it up like this. So the short version of this topic is Anytime you have the square root of a negative, you pull out the square root of -1. Pardon me, I made a mistake there. You pull out the square root of -1 and then whatever's left. And we know from this definition, square root of -1, that's what we call I. In this case, the square root of 4 is just 2. And we'd always write it with the regular number first and then the I. And if we try to go backwards, we say, okay, well, this is the square root of -4. Okay, so if we square it, then we should get -4. Well, let's see how that works. 2 times 2 is 4. I times I, well, we know what I squared is. It's -1. So it works. Okay, let's do another one. Let's do square root of -8. Every time we have the square root of a negative, first thing that we do is take out square root of -1. Then we have whatever's left. This becomes I. This we just learned how to do. Pause the video if you want to take a minute on this. But we know we can separate this into a perfect square. And then we have 2 left over. So we end up with, that's 2, that's I, and then root 2. And that is the order that you write it. Everything outside of the radical, starting with regular numbers, then imaginary ones, and then everything inside the radical. Okay, we'll do a couple of practice ones on the next page here. I'll put square root of -18 and square root of -72. Again, might be a good place to pause the video and give these a try. And now that you're back, every time we have the square root of a negative, we know how it's going to start. Take out square root of -1. So that's I. And we can just evaluate this like a regular radical because that's what it is now. We know there's a perfect square that goes into this. 9, so we'll separate into root 9 and root 2. And again, putting the parts together, that gives us 3, then the I, and then the root 2. For root -72, this is one that's a lot easier if you see that there's a big perfect square that goes into it, 36. So we separate into root -1 and 72, that's I. This separates into root 36 and root 2. So we have 6 there, then I, and then root 2. And that would be our final answer. So that's the combination of radicals and imaginary numbers. You can see why they go together. And these are our techniques. If it's a regular radical, always find the biggest perfect square that you can take out of it. But if you can't find the biggest square that you can take out of it, you can still do it. It'll just take a couple more steps. And anytime you have the square root of a negative, start by taking out square root of -1, that becomes I, and then do the rest of the radical the same way that you were doing the positive ones before.